So till now the data structures that we have covered, these are the linear data structures. Okay. What do we mean by linear data structures? All the elements that we have stored, they have one specific order. Okay, so in case of array, we had the elements in a particular order, and we were accessing them using an index, that is index 0, 1, 2, 3. Okay. In case of list, we had these nodes pointing to each other, and these nodes again, they had a particular order to them. Okay, so let's say this is the last node and this is my head node. So even list has a specific ordering of the elements. In case of stack, we still had the ordering based on the entry time, if you remember. So the element with the oldest entry time is at the bottom, and then we have elements with more recent entry time at the top, and the top one is the most recent element. So again, there is specific ordering of the elements. Similarly, in case of queue, we had this ordering, right? So we had the head of the queue and we had tail of the queue, and this is where we had the element with the oldest arrival time, right? And then we were having elements with more and more recent arrival time. So whenever you add towards the tail. Whenever you delete, you remove from the head. Okay. So all four of them, they have the complete ordering of the element. Okay. So now we are going to talk about how to search in these linear data structures. And the way stack and queues are defined, we are not supposed to have access to all their elements. In case of stack, we are supposed to have access only to the top element, and in case of queue, we are supposed to have access only to the head element. Okay. So we'll keep these two abstract data types out when we discuss about search. But now let's discuss about search on arrays and list. Okay. So let's first have a very naive and simple method. Okay. But before we define the method, let's understand the operation in terms of input and output. So we are going to say that when I define search, so if I'm talking about say array dot search, what I'm going to do is I'm going to take input a value, and then I'm going to return the index of the element where the element is present. Okay, so that's the way it is going to work. For example, in this array, let's say I have values 5, 29, 38, 66, and I search for value 38, then the result is going to be 2, because 38 is stored at index 2 in my array. Okay, so the way search is going to work on arrays is it will return me the index if the given value is present. However, if the given value is absent from the array, I'll be returning a special value. Let's call it -1. Okay, or let's call it error. Okay, so it would indicate that, oh, the search failed, the search could not locate that particular value in my array. So how should we perform the search operation? There could be a very simple naive method. I can say that, well, let me search the value in index 0, index 1, index 2, index 3, and so on. I will go right till the end of the array. So this is the linear search method. Okay. So if array has n elements, this method in worst case would require of the order of n operations. So this linear search method, it belongs to theta of n in case of arrays which are implemented as contiguous memory cells. Okay. Now let's ask the question, what if there are multiple copies of the value in my array? So in that case, I'm going to define my search behavior as, well, whichever copy you can find first, I'm fine with that. Okay. For example, I might have 2 copies of 66 in my array. Okay, so instead of 29, let's say I'm storing 66 here as well. And the way I have implemented search operation, let's say it starts searching from the end of the array. In that case, I'm going to retrieve the second copy of 66. So again, it is up to you how you define the behavior of your search. Okay. So sometimes I might want to define the search in such a way that if I give you a value to search, if you find the value in the array multiple times, still return me error. Okay. So in case the value is absent, I need a separate code. In case the value is present multiple times, I need a separate code. And if the value is present only once, I need the index. Okay. So how exactly search is supposed to behave? Well, it's up to you how you define. Okay. But let's start with a very simple behavior of the search. We'll say that if the value is absent, we will return a negative value. If the value is present, we'll return the index of the first element that we could find. We are not going to make any commitment about whether it is going to be the first copy or the last copy or anything. Whichever one we encounter, we are going to return it. Okay. So that's the way we have defined array search, and it takes theta in time. Okay. Now let's talk about list.search. So if I give you a list and then I ask you to search for a particular value v. Okay. So this value v is different from the address of the node. Please understand that. So the list, each node has a certain address which corresponds to the memory location where this whole node is stored. But inside the node, I will be storing certain values. So I might store 6, 12, and I might store 5. Okay, so we are searching for a value. Okay, so let's again define the behavior of this search function. So we'll say that if I'm trying to find a value in my list, if I fail to find the value, I'm going to return a null pointer, indicating that I could not find the value. In case I can find the value, I will return the address of the node where I could find the value. If the list contains multiple copies of this particular value, I am not going to make any commitment about which of those copies are reported. It could be the first copy, it could be the last copy, it could be somewhere in between. There is no specific commitment. But I will ensure that the address that I return will definitely contain the value v. Okay. So let's think about our list and start with the linked representation of my list, and specifically the singly linked list. So if I have value v to search, all I have is pointer to my head node. So I'll start from the head node and I'll traverse each element of the list one by one using the next pointer that I have. And every time I visit a node, I'll compare the search value v with the contents of the node. So in the worst case, what will happen? I might have to go right to the end of the list. So even in this case, we are going through the complete list, and this is again a linear search algorithm. Okay. So if the list contains n elements, in the worst case, I will require of the order of n operations. And again, the linear search on my linked list belongs to theta of n. Now instead of singly linked list, if I have a doubly linked list, does it help me in any particular way? If you remember, the doubly linked list was helping us to traverse the list in the reverse direction efficiently. So with doubly linked list, when I try to search, I have option of searching from the beginning as well as searching from the end. But still that does not affect the time complexity. My search operation will still remain theta of n because no matter from where you search, in the worst case, you will still have to visit all the elements of your list. Okay. So you might say that no, because I have doubly linked list, I can simultaneously search from beginning and from the end. But still it does not help, because at each step you are going to compare with two nodes, and in the worst case you have to search till you reach to the middle of the list, which means that in the worst case you are still going to visit all the nodes of your list. Okay. So doubly linked list doesn't give us any advantage as far as improving the asymptotic time complexity of the search operation. However, let's think about a possible way to improve the efficiency of my search operation. What if all the elements in my linear data structure, array and list, they are arranged in a certain order, and then this order can help me to reduce the asymptotic time complexity of my search.